This video is going to introduce you to a cost-effective, double-layered coating method by using radiative cooling. Before we start, there is some background information that might help you understand the process better. The largest cooling power demand usually occurs at daytime under direct sunlight. Imagine there is a roof with a control volume around it. There are sources coming in and out the control volume, and we're interested in finding the net cooling power, P net in this case. First, we have absorbed solar power, P sun. Also, there is absorbed power from the atmosphere radiation, PATM. In addition, we also have absorbed power due to convection and conduction. Last, we have power emitted by the roof. Our goal is to maximize the net cooling power, P net, so that we can cool the surface as much as possible. In order to do this, we can increase the emitted power, P rad, and decrease the solar power, P sun. From surface energy balance, we know that absorptivity plus reflectivity plus the transmissivity should equal to 1. If we want the emitted power from the roof to the deep sky without any interference from the atmosphere, we should make sure that the transmissivity is equal to 1. Absorptivity is equal to 0 and reflectivity is also equal to 0. These properties are present when the wavelength is in between 8 to 13 micrometers. Therefore, our goal is to find a material that can emit the maximum radiation within this range. Currently, carbon black is a good candidate because it has a very high emissivity between 8 to 13 micrometer wavelength. In addition to maximizing emitted power, it is also important to decrease the amount of power absorbed by the roof from the sun. According to the equation that you see, the solar power is equal to absorptivity times radiation. In order to reduce solar power, P sun, we can minimize absorptivity alpha. The sun emits the majority of its power within the 0.3 to 2.5 micrometers. Therefore, our goal is to find a material that has a low absorptivity in this range, which means a high reflectivity in the spectrum. Titanium dioxide of Ru2 phase is a good option due to its high reflectivity in the solar spectrum. The current way of implementing these two materials is by embedding titanium dioxide particles in acrylic resin on the top and carbon black at the bottom. Currently, with the particle radius of 0.2 micrometers, this coating can reflect 90% of the solar power and can almost behave like a black body with an emissivity bigger than 0.9. I hope you enjoyed the video and hope it helped introduce you to the concepts behind radiative cooling. Thank you.